It's one of the biggest mysteries in science. It's the elephant in the room that you can't see. It makes up the majority of the universe, 70%, the other 30% being ordinary and dark matter. But we don't really know what it is. It's as if we're boats sailing on an invisible ocean, trying to figure out what the heck we're sailing on. The burning questions we want to ask are, what is dark energy? What could be causing it? Why is it there? And finally, does it really exist, or could our measurements be completely wrong? Before we start answering those questions, I want to take a moment to tell you about the sponsor of today's videos. If you like my videos, then you're going to love Magellan TV. Magellan was founded by filmmakers and producers who bring premium, in-depth documentary content. This video and the prior two videos were inspired in part due to a series I watched on Magellan TV called Space, The New Frontier. There's a fascinating episode called The Dark Side, which talks about the mystery of dark matter and dark energy. Check it out when you join. Besides space, other featured subjects on Magellan TV include history, nature, and of course science. You can watch it on all your devices as well as your TV anytime without any ads or any interruptions, and in 4K. I'm delighted to tell you that Magellan TV has an exclusive offer right now for Arvin Ash viewers. If you use the link in the description, you'll get a free 1-month trial. I highly recommend Magellan TV, but be sure to use the link in the description. Ever since 1929, when Edwin Hubble discovered that the universe was expanding, scientists have sought to find out what this expansion rate was. Most scientists believed that while the universe was known to be expanding, this expansion rate had to be slowing down over time because of the attractive nature of gravity, pulling matter together. So scientists set out to measure this slowing down of the expansion rate. This was not easy to do because in order to make these kinds of measurements, you have to be able to view the brightness and redshifts of galaxies that are hundreds of millions and billions of light years away. These are objects in the sky that we cannot see with our naked eye. There was no good way to measure this accurately for most of the 20th century until very large telescopes and the Hubble telescopes were built. In addition, some kind of measurement technique was needed to establish a standard luminosity that these galaxies could be compared to, because not all galaxies are equally bright at the same distance. This standard luminosity is called a standard candle. In the late 1980s and early 90s, two groups of astronomers, one led by Saul Perlmutter and Adam Rees in the US, and Brian Schmidt in Australia, came up with a clever way to measure the true distances and redshifts of very distant galaxies by trying to find recent supernova explosions, very special ones called Type 1a supernova. These provide a standard candle because all Type A supernovae explode with the same luminosity because they grow to about the same size. So by measuring the brightness of these supernovae, scientists can ascertain the distance. And by measuring the redshift of this same light, they could determine how much space had expanded from the time the light left the supernova. When these two pieces of data were combined from galaxies that were at various distances from Earth, they could get an idea of how much space had expanded over different time frames, and thus how fast the galaxies were moving away from Earth. What they found was shocking to most scientists because not only was the universe not slowing down or remaining constant, it was speeding up. The expansion was accelerating, and no one could explain it. Saul Perlmutter, who won a Nobel Prize for this discovery, described this as throwing an apple in the air, waiting for it to come down, only to find that it took off like a rocket into outer space. So the question is, if it took off like a rocket, where did the energy come from to fuel this rocket? This apparent energy that is fueling the accelerating expansion of the universe is called dark energy. So what could be causing it? There are three possibilities. The first possibility is that this energy is a property of space itself. Now, this was buried in a version of Einstein's equation of general relativity that contains something called a cosmological constant. It's represented by the Greek letter lambda. Ironically, Einstein had introduced lambda to counterbalance the effect of gravity to keep the universe static. He abandoned it after Hubble's discovery of the expansion of the universe, calling it his greatest blunder. Lambda can be thought of as the energy density of the vacuum of space, what we perceive as nothing. It comes from a non-perfect cancellation of quantum fluctuations. What do I mean by this? According to Heisenberg's uncertainty principle, quantum fields from which all particles come from cannot sit still. These fields are constantly creating virtual particles in empty space. So for example, electrons and positrons, protons and antiprotons, quarks and antiquarks come in and out of existence in empty space. This can be seen from this version of Heisenberg's equation. The change or uncertainty in energy times the uncertainty in time is greater than or equal to Planck's constant divided by 2 times pi. This equation also tells you that you can have virtual particles come out of nothing if the change in energy and/or the change in time is so small that it is less than Planck's constant over 2 pi. These virtual particles are not something that you can see. So is there any experimental evidence that can attest to the fact that this energy exists? It turns out there is, and it's called the Casimir effect. I talked a little bit about it in my warp drive video, but essentially it's a physical effect that you can see and feel due to the fluctuations of quantum fields in empty space. So there is some experimental evidence that this actually exists and can have positive energy. But the biggest problem with this theory is that when you use the known equations of quantum mechanics to calculate what this energy should be, the theoretical energy is almost 120 orders of magnitude higher than what is actually measured from type 1a supernova and the cosmic microwave background. This is the greatest mismatch between theory and observation in all of physics, the worst prediction of all time. In other words, our equations indicate that this energy should be much larger than what it actually is, but obviously our equations are wrong because if the energy was as much as theorized, the universe would have expanded so fast that galaxies and solar systems and we would not exist. So the vacuum energy is close to zero, but not quite zero. Why is this the case? Why is there just enough vacuum energy to cause the expansion rate to be just what we observe it to be? One scenario could be that maybe the vacuum energy really is zero due to some overlying symmetry in the universe, which we don't understand yet. But the slight amount of remaining dark energy is explained by some other mechanism. The most extensively investigated alternative mechanism to quantum fluctuations is a set of theories generically called quintessence. This is similar to Aristotle's fifth element, essence, the other 4 being fire, earth, water, and air. Quintessence would be like an extra energy field that pervades the entire universe, which happens to be repulsive. This field would be almost the same throughout space and throughout time, but not exactly the same. It is something that can change slightly in time and can fluctuate from place to place. Unlike lambda or vacuum energy, which is the same throughout the universe, it would be a dynamical dark energy. In other words, it can change slightly from place to place and in time. The interesting thing about dynamical dark energy or quintessence is that it can be measured. How? Because the difference in dark energy in different parts of space would be measurable. And if it is found to be true, it would eliminate the idea of the dark energy emanating from quantum fluctuations. It can be thought of as a 5th fundamental force, the other 4 being gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. This would be a force mediated by a new boson particle. Now, there is a fine-tuning problem that I want to mention here, which is called the coincidence scandal. If you look at the current measured energy density of the universe, you see that dark energy consists of 70%, and the matter density is the other 30%. These are really almost the same in the grand scheme of things. 30% is almost 70%. The difference between the two is only about 2.3. The reason this is considered coincidental is because the dark energy density of the universe is staying constant from moment to moment, but the energy density of matter is going down dramatically because as the universe expands, the energy density of matter goes down. Matter becomes less dense as space expands. If you go back to the time of the cosmic microwave background, 380,000 years after the Big Bang, the matter density was about 1 billion times more. So the ratio between the two was about 1 billion. And in the future, the difference between the two densities will also be dramatic. Why do we happen to live in a moment in the history of the universe where the difference is only about 2.3? Why should it be that way? It seems like a profound coincidence. If we go with the dark energy model explained by vacuum fluctuations, which predicts that dark energy stays exactly the same throughout space and throughout time, then you have to concede that there's really something special about now. But if you believe quintessence is true, then you can say, hey, This is not really a coincidence because dark energy is dynamical. It can change. And there's some underlying mechanism that has made it so that the energy density ratio right now is only about 2. What would we see if we could detect this quintessence field? For one thing, if the field exists, it would be slowly going down in value over time. We would see it as a decrease in dark energy density over time. But there's another way that quintessence could be detected. The excitations of the quintessence field would manifest itself as a particle, probably a boson, but unlike every other boson, it would have negative energy. So in empty space, you could create some positive energy particles and some negative energy particles without violating conservation laws. This would mean that lighter particles could decay into heavier particles by emitting quintessence particles with negative energy. Of course, this has never been seen, but if we were able to harness it, we could realize Zefram Cochrane's dream and the dream of Star Trek fans everywhere, because we could finally build that warp engine and start our 5-year mission to other worlds. But so far, attempts to explain or detect quintessence have not worked. The models that fit the current data indicate that dark energy is not dynamical, but stays constant throughout space and time. Could dark energy be photons or radiation? No, because the density of photons and radiation goes down as space expands. Dark energy, however, stays the same. So as more space is created, more dark energy is created. Why is it that if the density doesn't go down, it still makes the universe accelerate? Because what it means is that every cubic centimeter of space is expanding at a constant rate. So over very large distances, the cumulative effect is an acceleration of the universe. As more space is added, more energy is added, and the result is accelerating expansion. But you might say, if more energy is being created, doesn't this violate energy conservation? It turns out that it does not, because the positive energy is perfectly balanced by an increase in negative gravitational energy of the universe. This can be thought of like lifting a ball off the floor. The energy that you are adding to the ball is balanced by the negative gravitational potential energy of the ball. Now, the third possibility is that maybe we are all wrong about dark energy, and maybe it doesn't exist at all. There is a small minority of scientists who believe this. Most notably among them is Subir Sarkar, theoretical physicist at the University of Oxford in the UK. His group examined the Type 1a supernova data after the raw data was made available to the public in 2014. He argues that the original supernova data were not compelling because they had a correlation of only 3 sigma instead of the typical standard for cosmology, which is 5 sigma. In addition, he argues that the original calculations did not take into account the uneven distribution of matter in the universe. If the Milky Way itself is being pulled in one direction, then this would cause an error in the measurement. In other words, maybe we are the ones decelerating instead of the rest of the universe accelerating. Given these potential errors, he says the original data correlation is likely to be even lower than 3 sigma, more like 2 sigma. He therefore believes dark energy may not exist. Dr. Sarkar is firmly in the minority on his views for several reasons. Scientists knew from the very beginning that it was 3 sigma data. So this is not new information. By the way, 3 sigma data still correlates at a reasonably high 99.7%. 2 sigma is 95%. Cosmologists prefer 5 sigma, which is 99.99997%. But even at a 2 sigma correlation of 95%, there is significant correlation. Part of the reason cosmologists readily accepted this data back in 1998 is because prior to this, cosmological models predicted that the universe had something called a critical energy density, which means that it was not curved in 4 dimensions, it was flat in 4 dimensions. But the matter only accounted for 30% of this critical density. So the remaining 70% of the energy density had remained a mystery. So when the supernova data indicated that the amount of dark energy needed to make the universe accelerate is precisely 70% of the critical density, the mystery of the missing 70% energy was solved. And it was a eureka moment for scientists, and everything fell into place, and physicists quickly adopted this dark energy model. The other fact is that the 1998 supernova data is not the only data that provides evidence for dark energy. Subsequent independent studies have confirmed this, in particular the 2000 cosmic microwave background experiments and the Sloan Digital Sky Survey in 2003 showed strong evidence that the matter density of the universe is about 30% of the critical density, meaning 70% dark energy is needed to justify what we observe. So dark energy makes many of the puzzle pieces fit together to tell a story that is consistent. This is why attempts to discredit dark matter are not generally accepted. You could still say, what if everybody is wrong? Maybe the universe is not flat, or maybe there is something wrong with Einstein's theory of gravity. You could be right. But when scientists attempt to modify general relativity, it causes a problem and the whole equation breaks down. So for now, what is generally accepted is that dark energy exists and it fits with both our observations and the best models of cosmology. So unlike what Aristotle believed, we're not only not the center of the universe, we're not even made of mostly the same stuff. We're made of only the minuscule 4% that the universe is made of. Arvinash here. If you like our videos, then consider subscribing and ring the bell so that you can be informed when we upload more fascinating videos. We'll see you in the next video.